In this video, we will talk about types of discontinuities. So I want to look at an example where we have this graph, and this graph has all sorts of discontinuities. So I want to first have you pause the video for 1 minute and see if you can list all of the x values where this function is discontinuous. 4, 3, 2, 1. Pause it for 1 minute and list all the x values where this is discontinuous. Alrighty, so hopefully you did that. Hopefully you paused it and wrote those x values. Let's talk about it together. So one of those is, I'll put a bullet point next to it, x equals -4. Our function is definitely discontinuous there. And at -4, what I have is a hole in the graph. The technical term for that is a removable discontinuity. And what makes something removable is the fact that we can fill it in, we can make it continuous, we could fill it in by drawing / moving one point. So in this case, if I were to draw in a point right where that hole is, it would make it continuous. What I mean by moving is, if there was a point already defined where x equals -4, if I would move that down to where that hole is, it would make the function continuous. Okay, so that is what makes something removable. So this function has one other removable discontinuity. It's at 7. X equals 7. This is also a removable discontinuity, and that I can make the function continuous there by just moving where that defined point is at 7, by moving it and filling in that hole. All right, so there are two other types of discontinuities. There's one at x equals -1. Have this vertical asymptote, and on either side the function is doing some sort of infinite thing, either going down to -infinity from the left or up to +infinity from the right. So this is called an infinite discontinuity. An infinite discontinuity. And graphically at infinite discontinuities, there is a vertical asymptote. So a vertical asymptote. Okay, and then one final type of discontinuity we have at 3. And at 3, the function kind of goes on the left-hand side to where this hole is, and then it jumps down to where that closed circle is and picks it up. And this is called a jump discontinuity. Because as we're drawing the graph, we would literally jump, as I trace it out, when we get to this hole on the left, down here to continue drawing the graph. All right, so this infinite discontinuity and jump discontinuities, these collectively are non-removable. They are non-removable discontinuities. One of the ways I remember removable versus non-removable is, I think about it as with the removable discontinuity, like at -4 and at 7, I can remove the fact that it's discontinuous by just drawing in a point. So at -4, drawing in a point where that hole is, same thing at 7, just drawing in a point, and that would remove the fact that it's discontinuous. At a non-removable discontinuity, I cannot remove the fact that it's discontinuous by just drawing a point. I can't do that with a vertical asymptote. No matter where I draw a point, it's still going to be discontinuous. Even at that jump, even if I were to sort of fill in where this hole is, it wouldn't get rid of the discontinuity. All right. Okay, so that was just a bit of terminology. Now let's do an example. Let's get more practice with continuity. So I'm going to let c of t be this function. Part A says, well, what is c of -3? Well, I just have to plug -3 into my function. So c of -3, if I plug it in, gives me 2 times -3 cubed plus 6 times -3 squared minus 4 times -3 minus 12 on the top. On the bottom, we get 2 times -3 squared plus 5 times -3 and then minus 3. Okay, so if I were to simplify this and work it out, the top is 0 and the bottom is also 0. which means c of negative 3, this is undefined. Okay, so when I try to plug negative 3 into this function, it is undefined. Part B now asks, how would you define c of negative 3 if we got to pick whatever we wanted to, have it be any value, to make our function continuous at t equals negative 3? Okay. Well, for a function to be continuous, remember the definition. I need c of negative 3. I need the y value of my function at that point to be equal to the limit as t approaches negative 3 of my function. Okay, so let's take this limit, and whatever that limit ends up equaling, if it's just some finite number, that's what we're going to set c of negative 3 to be. All right, so let's take this limit. The limit as t approaches negative 3. Remember, our function was 2t cubed. Let's move it up so I can see it. It was 2t cubed plus 6t squared. Let's zoom it out a little bit so I can see it. 6t squared minus 4t minus 12 over 2t squared plus 5t minus 3. And to evaluate this limit, I know that when I plug in, we got 0 over 0. So I'm going to have to simplify. Okay, so let's try to factor. We get the limit as t approaches negative 3 of, and now let's try to factor. I think the denominator is easier. It's just a quadratic. I'll get a 2t, I'll get a t, and I might have to play around with it a little bit, but if I put a 3 here and a 1 here, plus and a minus there, that ends up working to factor it. On the top, I have 4 terms. So a common strategy is we could try to factor by grouping. So maybe I'll group the first 2 terms together, and then the second 2 terms together. And if that doesn't work, then I'll try a different grouping, but maybe let's try this first. So in the first 2 terms, we could factor out 2t squared, and that'll leave us with t plus 3. From the second 2 terms, I could factor out a minus 4, and that'll leave us with t plus 3. It's a little bit better to factor out negative 4 than positive 4, because I notice now that, oh wait, this is the same as that. So because both of my groups have this t plus 3 in common, we can factor it out. T approaches negative 3. Let's factor out that t plus 3. And when it's factored, from the first group, I'm left with 2t squared. From the second group, I'm left with a minus 4. And on the bottom, we have 2t minus 1 times t plus 3. Now this is nice because I can cancel out the t plus 3's. And now let's plug in. So if I plug in negative 3 to the top, we get, let's see, 2 times negative 3 squared minus 4. On the bottom, we'll get 2 times negative 3 minus 1. So we get 2 times 9, which is 18, minus 4. 18 minus 4. And on the bottom, I'll get negative 6 minus 1, which becomes 14 over negative 7, which is negative 2. So that's what this limit is. This limit equals negative 2. So if I define c of negative 3 to be equal to negative 2, then the y value of the function at the point will be equal to the limit, and that'll make it continuous. So this is what I want to let c of negative 3 be. Visualizing this a little bit, if I were to draw some axes, we're taking the limit as t approaches negative 3, so I'll put negative 3 here on the x-axis. Even though my variable is t, it's kind of like t is my input, so this is the t-axis. And we just show that the limit is negative 2. So that means as you get close to negative 3 from the left side and from the right side, the y values get super close to negative 2. So maybe the graph looks something like getting super close like that. I know that when we tried to plug in negative 3 into the function, it was undefined. So because of that, I have to skip this point, and that's giving the graph a hole. Visually, this function over here has a hole like this. It has a removable discontinuity. And that's why I can make it continuous by just defining c of negative 3 in a different way. In this case, by letting it be negative 2. That would fill in that hole. So we have finished our second goal for this section, talking about how to classify the types of discontinuities a function can have.